continue to describe the basic mathematical model to describe a physical random experiment. All right, and so last Tuesday we defined the sample space as well as sigma algebra, and we know sigma algebra is a collection of events of interest. Okay. So given a sample space called X and a sigma algebra called F. Right, and we know we have defined that it is a sigma algebra is a well-structured collection of events of interest. Okay, by the way, I try to make my character bigger. But if you can't see it clearly, let me know, because sometimes I write my lectures and the lectures become smaller and smaller. Okay, so just remind me, okay, please. All right, so it's well structured. So we say actually there are three requirements, three properties, right, for a sigma algebra to satisfy. First one is that the sample space should be included in this collection, and the sample space will be called the total event. This is the first property. The second property is that if the sigma algebra has an event E, then the complement of E, not E means not E, should be also a member of in the sigma algebra, right? This is the second property. The third property is that if we have a sequence of countably many events in the sigma algebra F, then their union should be an event in F. Okay, so we have three property, and as I just mentioned on Tuesday, that is because for the logical reasoning. Okay, for the sake of logical reasoning. All right, and so now suppose we have a sample space X and a sigma algebra F. Okay, and all right, and we also call events of interest measurable subset of the sample space. Okay, we also call it measurable subset. Because that the assignment, so in probability, a main task is to assign probability. So the assignment of probability to events in the sigma algebra F is a mapping. All right, we call P from the collection of events of interest, the sigma algebra, to the set of all non-negative real numbers. All right, so actually it's a mapping because for each event in F we will assign the probability. Okay, and so which satisfy the following 3 we call intuitive axioms. Okay, so the axiom number 1 we call non-activity, which says that for all events in the sigma algebra, okay, the value of the assignment should be greater than or equal to 0. Because probability, as our understanding, it should be non-negative. Okay? So that is axiom number 1. Axiom number 2 is called normalization right? The probability assignment to the total event should be equal to 1. Okay? The third one, axiom number 3, we call countable additivity. Okay? So for any sequence of mutually exclusive events, E1, E2, so it's a sequence. Okay? So it's countable, right? Maybe infinite, but it's just a sequence. And mutually exclusive means that for each EI, the intersection EJ, okay, the intersection is the empty set, okay, for all I not equal to J. Okay, so they are exclusive because mutually, because that any two of them have empty intersection. Okay, so that is the meaning of exclusive, mutually exclusive. Right. So for any such a sequence, the probability of their union okay, or maybe I use I would be enough. Now, because that we have a sequence of events, and by the third property of sigma algebra, this union must be in F again, right? Okay, so it's in the domain of this mapping. Okay, of this mapping. So P is go to, right? So the probability, the assignment of probability is a mapping, okay? So it's a function. So the domain is the collection of all events of interest, okay? And the codomain is the set of all non-negative real numbers, okay? Just an ordinary function. But such an ordinary function should satisfy 3 axioms. Okay? Okay, so this union is become to the sum of the probability of individual events EI. Okay? So this is also intuitive. Okay, so because this is the probability that any one of the, because the union means any one, right? At least the one of the event to occur. right? And so, and because that these events are mutually exclusive, all right, so they will not occur simultaneously, right? It's impossible because the intersection is empty, okay? And so that the probability of at least one of the mutually exclusive event to occur is equal to the sum of the probability of individual event EI. Okay? So this is called countable additivity. Any questions? All right. Now we take a couple of examples. Okay. For example, flipping two coins. Okay. Suppose we have two coins, and we know a coin has two faces. One is called head face, the other called tail face, right? Actually, so they are head and tail, and we have two coins to flip. So what are possible outcomes of this random experiment? All right. So now, so what is that? So what is the sample space? Well, sample space can be represented by a pair. Okay. So this is the face of the first coin, and this one is the face of the second coin, because we have two coins, right? So that this head or head, or tail, head or tail. So there are only 4 possible outcomes. So the sample space has a size 4. It's a very simple sample space. And in this, so it's a discrete type problem. And usually, right, we take the event of interest will include all possible subsets of the sample space, right? Okay, so that it's a power set of X. Okay, and as we know, the size so the size of the sigma algebra is small, just 16 only. So we have only 16 possible events to consider. Okay, so this is not a complicated problem. Questions? No? Okay. So now we want to give a probability assignment. Okay? So what is the reasonable probability assignment for you? Well, and so the probability assignment can be the following way. Suppose that the coins actually it's well manufactured, so that each coin to have the face to be head or tail, well, equally likely. Okay, suppose that they are equally likely. Okay, so that the outcome by symmetry that should to occur has equal probability. Okay, so that one of the possible assignment is can be okay. So for every singleton, okay, a singleton means that an event with only one possible outcome. Okay, and so this assignment is one fourth. Okay, for all outcome in the sum space. In the sum space there. Okay, and what is that? This is actually 1 over the size of the sum space. All right, and you can check axiom number 1. Okay, so in this case, with that, so that our definition is that the P from F to R, all right, and so for every event, the probability of the event will become to the sum defined okay. And what is that? This is actually because at every singleton has equal probability, okay, and so that so this is 1 over the size of X of the sum space, and the summation is sum over omega outcome in the event. So we just count the outcome, the number of outcomes in the event. So this becomes this ratio. Okay. All right. So with this understanding, so our decision to the probability assignment is here. Is that for every event, the probability assignment is just, so you can say it's a definition. Okay? It's just your assignment, right? All right, and so let's say, this is indeed a probability assignment. Well, let's go back to here to check. Non-negativity, yes, because by this definition, the value is a non-negative number. Okay, for example, if E is the empty set, then this is 0, right? But if E is not empty, this is positive. Okay, so negativity. How about the normalization? Well, if E is the total event, so if E is S, this is equal to 1, right? So it satisfies axiom number 2. How about 3? Countable additivity. Well, any sequence of the event and mutually exclusive. And you can see that if you consider a sequence of mutually exclusive event, but you can see the sum space has only 4 possible outcomes. So in such a sequence, except the first events, all other events should be empty set. Right? You can imagine that all other events is in the tail, they are all empty set. All right? And so you can see by this assignment that we just count the number of events so that so if they are disjoint unions, okay, and so axiom 1 and 2 are satisfied automatically. Okay, and now if E1, E2 are mutually exclusive, okay, then the size of the union is equal to the sum of the size of EI. Is that okay? And almost all the EIs are empty sets, so the size is zeros. Oh, I'm sorry. Infinite. Sorry. Okay. So they say from here, almost all EI are the empty set. Okay? Okay, so this is the same here. And so this implies that the probability of union, okay, is equal to and this is a summation and this is and we have done. So we prove that, we show that, okay, axiom number 3 is also satisfied. Okay? So we show that with this definition or this assignment, okay, the axiom 1, 2, 3 are satisfied. So this assignment is indeed a probability assignment. And because the assignment is according to the counting, so this probability is called a counting probability assignment. So counting probability assignment is based on the idea that here, but every outcome will occur equally likely. Okay, so this says that equally likely. So that is the basic assumption. So with this basic assumption, we then have this definition of the probability assignment, or sometimes we call probability measure, or we call, sometimes people call it probability measure. Okay? So every measurable set will be given a probability measure. Right. Questions? All right. Yes, please. Okay. The reason is here. It's here. If we consider a sum here, right? We consider here, this sum may diverge to infinity. But if almost all UI are 0, we don't worry about that. Because that, except a finite number of EIs, this quantity, this size are all zeros. So when you add 0, 0, 0, no matter how many how many zeros do you add, always 0. Yeah. So this is because of some mathematical rigors. Okay. Yeah. Good question. Other questions? All right. So, a further thinking for you. A cheating gambler may manufacture non-ideal coins. Okay. So that the probability for head is 1/2 probability for the head and tail, and the probability of is equal to 1/8. And the probability of tail is 1/4. All right, it's possible. All right, because if you are going to gamble with a gambler, okay, maybe he or she is a professional, and she or he would like to cheat with you, right? So he may manufacture idea or coins, and so he or she know a priori. I mean, you don't know it, right? And but he or she, the gambler, know that these two coin turns out head with half probability. Okay, and this is for these two possible outcome 1/8. But for this one, it's 1/4. So the gambler know that, but you don't know. So you may think about that it's equally likely, but the reality is this one. Okay, so please define a probability assignment our probability measure to model such a pair of coins. Right? Think about that. All right, so first thinking for you at home. I forgot it. Okay. You try. Think about it after class. Okay. And then with that information, suppose you know, right? Or suppose you are the gambler. Okay. So the gambler should, according to this prior information, right? he can build a probability assignment. Okay. So what is the probability assignment according to this information? You can construct. All right. So that is for you to think about it. Okay. So now you can see equally likely outcomes is one of possible model, measurement model, right? For a physical random experiment. You may have different measurement models if you know some prior information. Okay, so it depends on the material, okay, used in the physical random experiment. Okay, for this example, you manufacture non-ideal coins. Okay, and usually, even though my example is a little bit exaggerated, but in reality, this is actually an ideal case. Equally likely outcome is an ideal case. Any manufacturing should have defect. Okay, yeah. So that that is the gambling business again, right? Okay, the casino know all the theory behind it, and so you should know that. So in real world, not everything is so ideal. Okay. Okay. So, any questions? Okay. If no further questions, and before we go to a break, I would like to illustrate another example. Again, measuring the lifetime of a light bulb, okay, in working hours. All right, we already know that this is the sum of space is here, okay, and F sigma algebra, right? So if you still remember this example, F is the smallest sigma algebra. All right, the smallest sigma algebra of subset of X, which contains all intervals of the sum space. Okay, so we want to include all intervals of this sum space, right? To be events of interest or to be measurable subset, so that we can assign probability. Okay, so with that, so now how do we pick up a proper probability assignment or probability measure on event of interest, at least for all intervals of this semi-infinite interval here, from 0 to infinity. Okay, so now we recall calculus when you were in the freshman year. All right, so let f of x be a non-negative. Okay, so the value is non-negative. So non-negative valued, and the Riemann integrable. I believe you know a function is Riemann integrable, right? I believe. All right. Okay. For example, famous. For example, a non-negative valued continuous function. Right? So any continuous function is Riemann integrable over finite interval. Right? You should know that in calculus. Okay. Right, so on 0 infinity, such that the improper integral from 0 to infinity is equal to 1. Okay? So example, f of x is equal to e minus x for all x greater than or equal to 0. So this function, exponential function, they are non-negative valued, okay? So it's non-negative valued, and it's continuous. Okay, and so that it is Riemann integrable. All right, and this improper integral is equal to 1. How? Why? Well, if you take the okay, this is improper integral, right? And by taking the antiderivative, we have okay. So that we take the antiderivative, and what is that? So this is 1 minus e minus a here. And when a goes to infinity, this is equal to 1. So the improper integral is 1. Is that okay? All right. So this is just one of the possible examples, okay, for such a non-negative valued Riemann integrable function. Okay. All right. Then for any interval, we let the probability of AB, the probability of AB, the probability of AB, the probability of okay. So we have 4 types of finite interval. This is open interval, half closed, half open, half closed, and the closing interval here. And we define to be this definite Riemann integral. Okay? So this is the definite Riemann integral, right? Because A, B are finite. So this is always exist. Okay, so with that, then we will have a probability measure assignment. We call probability measure. P from F to plus. Okay, and the F here is the smallest sigma algebra of all subset of X contain all intervals. And so the event here will goes to the event. So the assignment and this is equal to okay, because the endpoint, if we include the endpoint, the integral is 0. Why? Because of this differential. dx is a continuous differential. Okay, so when you integrate over a point, then the integral value is 0. Okay, so that's why actually this 4 will have the same value. But they can be denoted this way. So we integrate over this interval. Okay, so in general, this is actually the integral of that, the definition. All right, and axiom 1 and 2 are automatically satisfied. Especially 2 is because what? The number 2 is because go up here, because this is and which is equal to 1. Okay? So this is the reason why we select such a non-negative valued Riemann integrable function. Okay? Because of we have axiom number 2 in our mind. So that's why we would like to select that. Okay? And it is non-negative because that it is non-negative. Non-negative, why is non-negative? Because f of x is non-negative valued. Okay. So the selection of f of x, this Riemann integrable function, to be non-negative value because axiom number 1 and satisfy this identity because of axiom number 2 in our mind. Okay? And axiom number 3 is satisfied because of the additivity of Riemann integral over non-overlap intervals. Okay? remember, in suppose we have A, B, C, D. Okay. Now AB, f of x, dx, plus CD, f of x, dx. Okay. So this is actually, say, AB, for example, plus, say, CD, for example, here. Okay, and this is actually the AB union CD, f of x dx. So the integral over a union of two intervals, if they are non-overlap, okay, then this integral is equal to the integral, the sum of the integral in individual interval. So that is the additivity of Riemann integral. Okay, of so it's a property of Riemann integral in calculus. Right, so axiom number 3 satisfies because that. Okay, and but the proof is a little bit intriguing, I know, because that as we mentioned, axiom number 3 is countable additivity. So you have to consider countable many mutually exclusive intervals, right? So you have to extend this only two, right? Two intervals, or finite number of intervals, right? To count many intervals. So you have to have such an extension. And so you have to overcome some of the technical difficulties, right? But I will, in this course, I will not go into the detail, okay? So if you have interest on this subject, I will recommend you to look at any textbook on advanced calculus. Okay, so you will have the answer in advanced calculus. But for the moment, please just give me trust me that yeah, this is true. We can prove that. Okay, because the simplest form is just the additivity of Riemann integral over non-overlapping intervals. That is the basic prototype of countable additivity here. Okay. Okay. So you have the nature. You can see that to give a proper probability measure on a physical random experiment, which has continuous nature, like the lifetime of light bulb, is actually a little bit difficult than discrete random experiment. Okay, but once we select a proper function like this one, f of x, like this, all right, then, and we are for sure know that we have a probability measure, and we make sure they satisfy these three properties, xm1, xm2, and xm3, right? Then we will have a well-structured mathematical model to analyze the random experiment. Okay, so okay, so let's have a break. Oh, great! So 1 minute more. All right, so let's have a break. Okay. Yes.
所以这个 f of x 的 f of x 是什么意思啊？
Okay, so let's continue our discussion. All right, so we have given two examples to illustrate how to construct probability measure. Okay, once we have a sample space, signal algebra, right? So now I would like to give a couple of properties. So the first one is proposition 2.3.8. When you look at A, B, C, D, it means some of the proposition or corollary or lemma that I give here for extra proposition or lemma or corollary. Okay? So not shown in the textbook, basically. Okay, so so for any finite sequence of mutually exclusive events, say E1, E2, up to En, i.e. EI, intersect with J is equal to empty set for all I not equal to J. But we have only a finite number of events here. And then probability of union I from 1 to N, EI, is equal to the summation probability of EI. Okay. So it's a consequence of, and I will show that this is a consequence of axiom number 3. Okay? So with that, EI equal to the empty set for I from n plus 1, n plus 2, Okay? Because this sequence is a finite sequence, right? So we have E1, E2 up to En, they are mutually exclusive. But when I insert infinitely many empty sets to form a countable sequence, right? Then we have for all I not equal to J, Ij equal to 1. We have I is also empty set. Okay, so now we construct a sequence, countable sequence, right? And still mutually exclusive. Okay, and so by axiom number 3, the probability of U I from 1 to infinity EI is equal to summation. Okay. But as we know, when I equal to n plus 1 and 2, EI is empty. So we know this is probability I from 1 to n EI. Okay. And this is implies that, oh, well, I haven't proved yet. Yeah, I'm sorry, I haven't proved that. Okay, I will prove that. Sorry. So this implies okay, maybe I should prove first. I'm sorry, this is my fault. Okay, so let me say this is B. I'm sorry, I will go back to that later. Okay, proposition. I'm sorry, I should prove this proposition first. Okay, so I have to show that. I have to prove that first. All right, so we let E1 to be S. Empty set. Okay? Then, so we let E1 is X, E2 is 3, etc. They are empty sets. Then EI intersect EJ is empty set for all. Okay. Is that okay? Now, so by axiom number 3, the probability of union is equal to summation EI. Okay? But this is the probability of X, so this is 1. Okay? So maybe I use another color to illustrate that. So this is the probability of X, and this is 1 by axiom number 2. Okay. And this is probability of X plus summation I from 1 to infinity probability of empty set. Okay. And so again, so this is 1 plus summation I from 1 probability of. Okay. So this is, and this is axiom number 2. Is that okay? Okay, so this is the price that. Zero. But this implies that, okay, number 1. By axiom number 1, the probability of the empty set is non-negative. And so when you sum over infinitely many copies of this number to be 0, the only possibility is that the probability of the empty set is 0. Okay, so that is the end of the proof. Okay. Okay, and so this is equal to right. So now we go back to here because we construct a countable sequence, right, of mutually exclusive event, right, by inserting EI to be empty set for all I from n plus 1, but etc. Okay, so we have that. Okay, and because this is equal to 0, so the sum is 0. Okay, so this is summation, and we have done. Okay, so for this finite union, okay, with mutually exclusive event, right, its probability is equal to the sum. This is finite sum of probability of the individual event. Questions? All right, so AB and C for event in the sigma algebra, the probability of E is in between 0 and 1. Okay? This is from the first inequality is from axiom number 1, right? So there is no doubt. So this is from axiom number 1. So we need only to prove the second inequality. All right, so since E union E complement is equal to S, and E intersect E complement is the empty set. All right, now, so we have two events, E and the E complement, and we'll apply proposition 2.3.b. So by proposition 2.3.b, okay, with n equal to 2. We only have two mutually exclusive events, E and E complement. And so our probability of E union EC is probability of E plus probability of EC. Okay? Now, but this is probability of X, and this is 1. Axiom number 2. So this implies that probability of E is 1 minus probability of E complement. Okay, and so this is equal to 1, since probability of E complement is greater than or equal to 0 by axiom number 1. And we have done. Questions? Okay, no question, good. Okay, so there are some simple properties. 2.4.1. Okay, in the textbook. All right, but this proposition has been proved already here. Okay, so I don't need to prove again. Okay, so the probability of E complement is actually equal to 1 minus probability of E. Okay. That is reasonable, right? Second proposition, 2.4.2 in the textbook, says that if E is contained in F, so F is bigger, E is smaller, then probability of E will be less than or equal to probability of F. Okay. And then we can draw the Venn diagram. I believe you know Venn diagram in high school. Okay. If you do not, please raise your hand if you know the Venn diagram. No one? Really? Oh, yes, thank you. Yeah, don't be shy. I believe you some of you know that. Good. Okay, Venn diagram is, okay, so this is called Venn diagram here. All right, E is smaller, right? And this is F. So F is bigger, E is smaller. So that is a Venn diagram. Very simple, very simple. Okay, and so why is that? Outside of the E, but inside of F. So this part is F intersect E complement. So sometimes this is called F minus E, okay? So F minus E means F intersect with the E complement here. Okay, so from the Venn diagram, it's easy to see that F is equal to E union F intersect E complement. Okay? And because E and F intersect E complement are disjoint, so we will represent this as the disjoint union. Okay? And for disjoint union, all right, so I will formulate the disjoint union of E and F intersect EC. Okay. So disjoint union is something. So let me give a definition of disjoint union, because I will talk about that quite often. A union is called a disjoint union denoted as if if EIs are mutually exclusive. Okay? So it's a kind of language, all right? Okay, so this is disjoint union. All right, so proof. Now we have so probability of F. Okay, since F is the disjoint union of E and F intersects E complement. Okay, from the Venn diagram. So by proposition, wow. Okay. Proposition 2.3.b. Okay, I'm sorry, I erased that already. Probability of F is equal to probability of E, disjoint union of F intersect is C. And this is probability of E plus probability of F intersect with E complement. Okay, so we have two events. These two events are mutually exclusive. Okay, so the probability of their union is equal to the sum of the probability of individual events. Okay, so we have that. Okay, and so this is equal to probability of E, since probability of F is greater than or equal to 0, and we have done, right? Because P of F, the probability of F is the sum of probability E and the probability of F intersect with E complement. Okay, so we prove the inequality. So if F is a bigger event than E, then the probability of F is bigger than or equal to the probability of event E. Okay, so that is proposition 2.4.2. Question? So they are all some easy applications of proposition 2.3.B. Okay. All right. So I have already used the notation here. Okay. Proposition 2.4.3 is that the probability of E union F is probability of E plus probability of F, okay, but minus probability of E intersection of F. Now look at the Venn diagram of this situation in general. So we have E have F here. So this is E in this. So here is E intersect F. All right, and this part. Okay. Now this is E minus F. This is F minus E. Okay. All right. So this is the Venn diagram. Right, so proof. First of all, the union of E and F is the disjoint union of E minus F and E intersect F and F minus E, right? So we can divide the union into 3 pieces. And these 3 pieces are mutually exclusive from the Venn diagram, because the Venn diagram gives you the membership of each set. A very clear graphical demonstration. Any questions? So this union can be expressed as disjoint union. Means union of mutually exclusive events. Okay? Question? No? Okay, good. Now, what about E? E has 2 parts, right? So E is E minus F, disjoint union into F. And also for F, F is F minus E disjoint E intersect F. Okay, so the idea is that we find some basic building block. Okay, we find 3 basic building blocks and use these 3 basic building blocks to build the union and the E and F themselves. That's all. And so now from the countable additivity or from the finite additivity, you can say so that probability of E union F is the probability of E plus probability of okay? First. Probability E is probability of E. And the probability of F okay? So they are all by proposition 2.3.b. And later on, we will call this proposition as the finite additivity of probability measure P. Okay, so we will, because later on I will forget proposition 2.3.b, something like that. But I always remember that this is called the finite additivity, right? A special case of countable additivity of axiom number 3, okay? All right, so now we have that, and so probability of E plus probability of F, you can add them together, so probability of E plus probability of E intersect F plus probability of F minus E and probability of E intersect F. But the first 3 is equal to the probability of E union F. Okay, so we prove that. So the addition of probability of E and probability F is equal to the addition of the probability of their union and probability of their intersection. Okay, and so that is the proposition. Okay, so that to write in another way, we have, so when we move this term to the left-hand side, so we have minus, and we have down. Okay, and this proposition can be extended, all right, an application of proposition 2.4.3 is to generalize is here to compute. Suppose we have the union of 3 events, and then now it becomes 2 more complicated. If you draw the Venn diagram, it becomes to be complicated, right? If you have 3 events, you become so complicated. And if you have, how about you have 100 events? That would be a huge task, right? All right. So that if we want to have something, some formula similar to this one, it means that we want to generalize this formula from 2 to 3. Okay. How can we do that? Well, if we have the experience of induction, okay, we can look at that. The 3 union by the associativity of union of set. Okay, you can think about the first union as 1. Okay, this is an event. Union is 3. Okay, so now we have 2 events. Okay, so this one is E, and E3 is F. Okay, all right. So when we apply the proposition 2.4.3, so we have three here. Okay. And now we apply the same proposition to this union, because now this is union E1 and E2. So you have E1 plus probability E2 minus probability E1 intersects E2. All right, and we have probability E3. How about this one? Well, you use the distributive law of intersection to the union. So the distributive law of the intersection to the union is that this is E1 intersect with E3, union E2 intersection with E3. Do you have any question about from to write this one to here? This is by distributive law of intersection to union. We have also another distributive law of union to intersection. Okay. But anyway. All right. So that is about set. Okay. Any questions? Okay. If no, now again, this is F. This is E and this is F, right? E and F. Okay. So we apply. So this is go to. So we apply proposition 2.4.3 again here and again here. So we apply proposition 2.4.3, this one, many times. Okay, but when we apply this one, I make arrangement PE1 plus PE2 plus PE3 minus PE1 intersect E2 minus here. This is PE1 intersect E3 plus PE2 intersects E3, okay, minus probability E1 intersect E3 intersects E2 intersects E3 here. Together. But this intersection is equal to E1 intersects E2 intersects E3. So So finally, we have PE1 plus PE2 plus PE3 minus PE1 intersects PE2 minus PE1 intersect E3, okay, minus E2 intersect E3, okay. Now, the last is plus PE1 intersects E2 intersects E3. Okay, so now we have a formula. The probability of the union of E1, E2, and E3 is equal to the sum of individual probabilities. And then minus the probability of mutual intersection. We have three, right? Three possible, because we three select two, right? So we have three possibility. E1 intersect E2, E1 intersect E3, E2 intersect E3. And then plus back. Because we minus too much, so we add something. And this one is the probability of the intersection of the three events. Okay? So in general, so that the temperature proposition 2.4.3 can be generalized to n events. Okay? With n events. So that is the proposition 2.4.4 is also called the inclusion and the exclusion identity. Okay? The inclusion exclusion identity says that inclusion, exclusion, and then inclusion. So that it says that the probability of E1 union E2 union union En. So suppose we consider the union of an event. Okay, then it is become to the summation of individual event. Okay, so this is inclusion, just like here. This is inclusion, and exclusion minus what? Minus pairs. So it is that is I1 less than I2, and the probability of EI1 intersect EI2. Okay. So you form pairs, and so this is exclusion. So this is inclusion, and then exclusion. And then here we now inclusion. So now we add summation I1, I2, I3, probability of EI1 intersect EI2 intersects EI3. And so intermediate term is that R plus 1, okay, for R, I1 less than I2 less up to IR, probability EI1 intersect EI2 intersect up to EIR. So we from an event we select all events. Okay? And then to form intersections. Okay? And so finally, so this is n plus 1, probability of E1, E2. So you take all the event, an event, to make the intersection. This is the last one. All right, so the formula, this is called inclusion exclusion identity. Okay? And so we can see how many terms do we have here. So in here, there are n sec 1 terms. Okay? In here, we have n sec 2 terms. Okay? In here, we have n sec r terms. Okay? And the proof, okay, it's exercise, homework, number 2. Okay? So when you look at homework number 2 assignment, okay, it's actually theoretical exercise 14. So you have to prove that by induction. Okay, and the basic idea is here. Probability in 2.4.3, right? When I derive it, right, the idea will be the same. Okay, so you have to prove that. Okay. Now we will derive some inequalities. Right. So we have identity, right? This is exact. But sometimes we can have identities. So from the inclusion and exclusion identity, okay, we have the following inclusion and exclusion inequalities. The idea is that because the identity involves so many terms here. What if we truncate the rest? Only the first, how about truncate the rest of the 10 except the first one? Is this one become greater than an inequality or not? If it's an inequality, what is the direction of the inequality? Greater than that? Less than that? How about if we truncate rate but leave the first two? Can we have another inequalities? Okay, lots of things like that. So we will prove, we will have the that I write here. All right, so the union. If we only take the first term, then we have inequality this way. Okay, so we have that. Okay, so this is called 2.1 inequality. But if we take the one inclusion, but the other exclusion, okay, so now if we include the second term here, then the inequality will change the direction. Because we subtract too much, okay? And so that we have to turn the direction. Furthermore, if we include okay? So if we include this term, we add back. Then we will add too much. So the direction become 2, etc. Okay? Up to the final term, we get the identity. Okay? So if we only include partial sum here, then we will have inequality with alternating directions. Okay? So we have inequality with alternating directions. Okay? Now we prove, oh, sorry. This is 2.2. This is 4.3. All right. So we will prove the first 3 and leave the rest for you. Okay. All right, so we observe that. The union of EI, right, from 1 to n, is equal to E1. And the disjoint union, see here, you have so suppose this is E1, E2, E3, we have etc. Okay, so let's see. E1. And the sum of the members in here is from E2, right? All right, but we will minus, so we will intersect minus EI, so we will intersect E1. Okay? Because we want to make this union into disjoint union. Okay, so once we have E1, okay, the contribution from E2 will be E2 intersects with E1, right? Exclude something in E1. Is that okay? So that is it's here. Okay, so this one is okay, so the contribution from E1 and E2 already here. How about the contribution from E3? Well, E3 will be intersect. Yeah. Oh, yeah, yes. Thank you. Thank you very much. Okay, and then the intersection of E1 union E2 complement, right? Because the contribution from E1 and E2 will be already here. So the contribution, thank you. So the contribution, so this is E3 intersect with E1 union E2 complement. Is that okay? So etc. up to En intersect with E1 union E2 complement. Okay? Do you have any difficulty? Okay, so they are all disjoint union. Okay. All right. So this is by finite additivity, the probability of union is equal to probability of E1 plus summation I from 2 to n, probability of EI intersect with E1 union union EI minus 1 complement. Is that okay? Okay, good. Now we solve for all. So now we compute this one. For all I in belong to n, we know PEI can be written as EI intersect with E1 union EI minus 1, okay, plus probability of EI intersect E1 union EI minus 1 complement. You look at think about the diagram. Suppose this is E, this is F. So now E can be decomposed into, so this is E intersect F. The other is this part. This part is the E intersects F complement. Right? So E is so that E becomes to union, disjoint union, complement. Okay, so they are disjoint union. That's why we have the addition. Because these two intersections are disjoint. Okay, so think about that. So this is E, this is F, this is E, this is F complement. Okay. Okay, so now, so you can see that this is what we want, right? And so that probability of I from 1 to n, EI, is equal to summation of I from 1 to probability of E1 plus summation I from 2 to n, probability of EI, okay, minus summation I from 2 to n, probability of EI, intersect the union. Okay? Is that okay? But again, by the distributive law of intersection to the union, so this is EI, so you can see that this is E1 intersects EI union, E2 intersects EI union, union, EI minus 1 intersects EI. Okay, and so it's better to write as the j from 1 to I minus 1, and the ej intersection ei. All right? So the final term so that probability of union I from 1 to n ei is equal to ei. So we put them together. So PE1 were included to this sum. So we start I from 1 here. And minus this term. I from 2 to n probability, the union of j less than j from 1 to I minus 1, and ej intersection ei here. But if we look at the union when I equal to 1, so to write it to include 1, now if I equal to 1, then this is 0. So this is an empty union. For an empty union, the definition is empty set. Empty union, right? So it's an empty set. Okay, so the probability is 0. Okay, so you can okay, so this is equal to the empty set. Okay, and so we can include them together. All right, so this is our identity here. And now, because this is probability, they are all non-negative. So from here, we prove so this is 2.1 things probability of is greater than or equal to 0. Okay, so we prove the first inequality. Okay, because of this identity. Okay, so this identity is quite useful. Okay. Okay. And so because of the time limitation, so please read the textbook for the rest of the proof. Okay. And right? So I leave you to self-study this section. But remark, it is similar to the example, of two coins in section 2.3. Okay. All right. So I have to stop. Okay. Yeah. Anyway, if you have any question about reading the rest of proof in the textbook, please raise your hand next Tuesday. Then I will explain the rest of the proof for you, okay? But so, and the 2.5, there are a lot of examples. So I will ask you to read through it. Okay? So I stop here.